Hi, this is Anil from University of Waterloo. I will be talking about our recent work on evaluating complex queries on streaming graphs, which will be presented as a part of ICDE 2022. This is a joint work with Angela Bonifati from Lyon 1 University and Tamarosu from University of Waterloo. So let me start with defining streaming graphs. We can define streaming graphs as an ordered sequence of tuples, where each tuple represents an edge, and each tuple is associated with a time step. In streaming applications, the scope of the application is usually bounded by using windowing construct, and in this context, the window defines a snapshot graph. Overall, two characteristics define streaming graphs. First of all, streams are unbounded, meaning that applications that process streaming graphs usually do not have access to the entire graph. Second, real-world streaming graphs have usually high streaming rates, requiring specialized solutions to ensure real-time guarantees. Let me provide some examples of real-world applications of streaming graphs. Consider an e-commerce application. We can model interactions between users and different entities as edges of a streaming graphs, such as credit transfers and purchases and reviews. Then the task of real-time credit card fraud detection can be modeled as a graph pattern, which is continuously evaluated over the streaming graphs. Similarly, on a computer network, node-to-node network communications can be modeled as edges of a streaming graph. Then the task of detecting denial of service attacks can be modeled as a subgraph pattern, which is continuously evaluated over the streaming graphs. A common theme that we observed in real-world applications is that these applications usually rely on specialized algorithms or techniques that are tailored for particular use cases and applications. And this is primarily because streaming graphs combine two difficult and challenging problems. First of all, these are graph queries that feature subgraph patterns and recursive path navigations. In some instances, these queries require returning and manipulating paths, essentially treating paths as the first-class citizens of the data model. We do have a number of systems that focus on processing graph workloads, such as graph databases or graph processing systems. However, these systems focus on the snapshot model. But these applications that process streaming graphs require queries that are continuously evaluated on fast-changing data. And the stream processing system provides the capabilities to deal with potentially unbounded streams and provide the primitives for online evaluation of queries to ensure real-time results. However, these systems do not support graph workloads. This is the main motivation of our paper. In the paper, our goal is to combine graphs and streams in a principal way with the purpose of designing a general-purpose streaming graph query processor. On a high level, such a general-purpose streaming graph query processing pipeline would look similar to a traditional query processing pipelines. A user query is represented on a high-level user language, is translated into an algebra expression. Then the plan generation module, with the help of the equivalence rules, generate the set of possible plans for the given query. Then the query optimizer, by either using cost models in statistics or using heuristic rules, create an optimized plan or choose the optimized plan from the set of available plans. Then the physical execution plan is generated by choosing the appropriate physical operator implementations. Finally, the execution engine processes this plan. Designing a general-purpose engine for streaming graph query processing requires rethinking these components in the context of streaming graphs. And in this talk, I will be primarily focusing on the plan generation and describing how to represent streaming graph queries and how to define the set of plans or the space of plans for streaming graph queries. In addition, I will be describing the generation of physical execution plans and the incremental evaluation of these streaming graph queries. Overall, in this talk, I will introduce our principled approach for processing streaming graph queries. I will start with defining the formal semantics of streaming graph data model and streaming graph queries. And on top of that, I will introduce the streaming graph algebra, which consists of a set of logical operators that enables us to formulate streaming graph query evaluation plans, and that formally defines the space of evaluation plans for these queries. And finally, I will describe our prototype implementation based on the timely data flow system. This implementation consists of incremental and non-blocking implementations of these streaming graph algebra operators. Let me start with defining our streaming graph query model. First of all, streaming graph is defined as an ordered sequence of streaming graph tuples. Each tuple represents an edge or a path in the graph, and each tuple is associated with a time interval, which represents the validity of that interaction. Then we can define a snapshot of a streaming graph as a mapping from the time domain to a finite set of streaming graph tuples. In brief, the snapshot consists of tuples that are valid at a given time point, and these tuples induce a directed labeled multigraph. This is important to define the semantics of streaming graph queries. But first, let me give you an example. I will use a query from LDBC Social Network Benchmark and the G-core query language to represent this query. Consider a recommendation task on a social network. We can define a recent-liker relationship as a triangle pattern that describes two users are recent likers of each other if a user follows another user and likes a content that is posted by that user. And for our recommendation task, we can say that we would like to find an arbitrary length of paths that consist of these recent liker relationships. Then we would like to recommend posts that are created by such users. And in G-core, we can represent this query by using a recursion over the path construct. In order to process this query over an unbounded stream, we can use a windowing construct to bound the scope of the query to the interactions that happen in the last 24 hours, for instance. And in the paper, we showed that we can define such queries by using a subset of data log that consists of non-recursive data log augmented with clean star. This particular subset corresponds to regular queries, and our model corresponds to streaming generalization of the regular property graph query language. And it is shown that this model subsumes existing graph query languages and is powerful enough to express queries that can be formulated in PGQL, Sparkle version 1.1, and Cypher. To define the semantics of continuously evaluating these queries over streaming graphs, we turn to the notion of snapshot reducibility from temporal databases. Given an output stream, as a result of a streaming graph query over an input stream, the snapshot of the output stream at any point in time is equivalent to the result of the corresponding one-time query over the snapshot of the input stream. The streaming graph query model enables us to represent or define the formal semantics of the class of queries that we target, but it doesn't describe how to evaluate these queries. And for this purpose, we introduced the streaming graph algebra. Window scan operator enables explicit representation of time-based sliding window by manipulating the validity interval of input stream graph tuples. And path operator enable representation of paths as the first-class citizens of the data and the query model by querying and returning paths from the input streaming graphs. Filter, union, and pattern operators have been studied before and are streaming generalization of similar operators in other query algebras. Combining these operators as a coherent and consistent query algebra to evaluate streaming graph queries is an important contribution of our work. Our paper includes more details and formal definitions of these operators, but here I want to provide an example. For this, I will use the same running query that I previously used. First, the window scan operator is applied over the input streaming graphs. Then we can use the pattern operator to define the recent liker relationship, which is defined by a triangle-shaped subgraph pattern between likes, follows, and post edges. Then we can find the paths of users that are connected by recent likely relationship using the pet operator. And finally, we can find the contents that are posted by such users by using the pattern operator. From this given algebraic expression, we can actually construct a query plan that consists of streaming graph algebra operators. In this query plan, leaf nodes represents the input graph stream, intermediate nodes represent streaming graph algebra operators, and the edges in between represents the flow of streaming graph tuples, or the streaming graphs. And in the paper, we provide a concrete algorithm to construct a logical query plan from a given algebraic expression. But it turns out that there can be more than one query plan for a given algebraic expression. For instance, for the pet query that consists of a clean star over the concatenation of three edge labels A, B, and C, we can create multiple streaming graph algebra expressions. First two corresponds to the existing pet evaluation methods in literature, the alpha relational algebra and finite automata. But on top of that, with the help of streaming graph algebra, we can actually find more algebraic expressions and more query plans for this pet query that is hybrid of these two approaches. And to systematically search this plan space for streaming graph queries using streaming graph algebra expressions, we define transformation rules on top of streaming graph algebra operators. These rules use particular algebraic properties of streaming graph algebra operators and enable us to represent equivalences between streaming graph algebra expressions, and enables query processor or query optimizers to systematically search this search space by using these equivalence rules. Overall, streaming graph algebra provides us the logical primitives to evaluate streaming graph queries. First of all, its operators and its transformation rules define the search space for streaming graph query evaluation plans. And in the paper, we formally prove the expressivity of streaming graph algebra by showing that we can find a streaming graph algebra expression for any streaming graph query. By decoupling the logical design from physical implementation, streaming graph algebra enables us to separate operator semantics from operator implementations, which I will describe soon. Being a composable query language with algebraic closure, we can form complex query plans using the small set of primitives provided by the streaming graph algebra operators. Currently, streaming graph query model and streaming graph algebra operators only support structural attributes to query the graph structure. Integrating attribute-based predicates to fully support the property graph model is a future work. Next, I will describe our implementation of a streaming graph query processor based on this algebraic framework. On the left, we have the query plan that is constructed by parsing the streaming graph algebra expression. On a high level, this query plan looks like a data flow graph. So an obvious question is that, can we execute streaming graph queries or these query evaluation plans using a data flow engine? To answer that question, let's first look at individual operators. The pattern operator in streaming graph algebra is used to find subgraph patterns, which are equivalent to conjunctive queries and can be evaluated using joins. So to evaluate subgraph patterns, the underlying execution engine should provide support for joins. The path operator is used to query recursive path patterns. So to support the path operator, the underlying engine should provide support for iteration or recursion. Also, streaming graph queries are continuously evaluated as the underlying stream changes. So the underlying engine should provide streaming support. So in principle, these query plans constructed from streaming graph algebra expressions can be evaluated on a data flow engine that supports incremental and iterative computations. Differential data flow is one such system, and it provides the primitives for incremental and iterative evaluation of general purpose data flow graphs. And we provided physical implementations of our operators by mapping them to differential data flow constructs, and we use that for our experiments. But the next question we'd like to answer is, can we do better by utilizing the structure of the streaming graph queries? First, from the formal definition of the streaming graph query model, we know that the recursion in streaming graph queries is limited to transitive closure, which is in the form of regular pet queries. So we can utilize streaming algorithms for evaluation of these regular path query fragments or evaluation of these recursive fragments instead of supporting general purpose recursion. Second, sliding windows have temporal patterns. Specifically, tuples expire in the same order they're inserted into a window. So operator implementations can utilize this pattern to eliminate the need for negative tuples to process expiration and can simplify the state maintenance. We implemented these ideas and compared against the differential data flow baseline using the real-world graph of Stack Overflow and the synthetic LDBC social network benchmark. Overall, we observed that these optimizations have significant performance benefits for the most queries we tested. Digging into details, we observed that using an automata-based regular pet query evaluation algorithm provides better performance on cyclic graphs compared to using fixed point iterations. And the use of direct approach or utilizing these temporal patterns of sliding window movements to simplify state maintenance does actually reduce the cost of expirations, but it can come with higher memory footprint. Please see our paper for more details on our experimental evaluation. To wrap up, the main motivation of our paper is to study combining graphs and streams in a principled way and to design a general purpose streaming graph query processor. And in this talk, I described how we need to rethink the components of a query processing pipeline in the context of streaming graphs. First, I focus on the representation of streaming graph queries and streaming graph query evaluation plans, and I described a formal graph query model called streaming graph queries and an algebra called streaming graph algebra. They provide us the logical primitives to represent query evaluation plans. Then I described our prototype implementation of a streaming graph query processor based on this framework. This query processor consists of non-blocking implementations of streaming graph algebra operators, and our experimental evaluation shows that by utilizing the structure of streaming graph queries, we can devise optimized implementations for these operators. We are currently working on designing cost formulas and statistics for streaming graph algebra operators for cost-based optimization of these streaming graph queries. In the future, we are planning to integrate attribute-based predicates to our query model and algebra operators to fully support the property graph model. Please see our project webpage to get more details on our work and to access relevant papers, code, and talks.